All right, so here's our problem. It's a frame with 3 separate point loads on it. We got dimensions. As we can see, our values right over here are all in kips and inches. Our loads are in kips, so that's fine, but all of our dimensions are in feet. I always recommend in the beginning of a problem, if you can, just to get in there and change those values to be all the same, so you minimize, sorry, having issues here, minimize any risk of accidentally using the wrong units and then therefore getting the wrong values for your answers. So let's just change this all to be in inches, so we just never have to worry about that. Very simple calculation here. Don't think I need to show you. So we're going to be using, to solve this problem, virtual work. So there's 2 different ways of solving in a problem like this. You can use this integration method using this equation right here, or you can do the graphical method. And we're going to do both. First, we're going to do the integration method. And so for a problem, it can depend. You can use either method, but depending on the problem, one of them is going to be easier and less time consuming. And as engineers, we will be busy, and it's being able to learn what is the most efficient and quickest way to solve a problem, what method we need to be using is pretty important. But for this, we're just going to do both of them because we're still in the learning process and we need to be comfortable with using both of these methods. So, as I laid out here, this is the procedures from the structural analysis understanding behavior book from Wiley that my class uses. I think this is like the last chapter for determinate structures. If you couldn't tell, this is a determinate structure. But all right, now that we've converted it, we can just jump into the problem following this procedure. First one, identify the appropriate coordinate system. So this just means when we are looking at the individual members, or we're going to be looking at the internal moments inside, what our value of x, what the coordinate systems for that value of x is going to be. So let's do this in red. First one will be here, be x1. And then we're going to do this anytime we're seeing some major discontinuity. So we can do x1 will go from A to B. Its bounds will be from 0 to 180 inches. Our next one will go from here to here, and it'll be x2. And it'll be stopping somewhere before this 20 kips, which would be the next discontinuity. And we could add for x3 to start at the same place as x2 and extend past the 20 kips. That would definitely work. I think for symmetry though, just makes sense to just have it right here. And we can probably see that once we develop those moment equations for x2 and x3 that they will be the same because of symmetry. So that's just kind of, again, making our job quicker. And then x4 will just be from here. I would like to know it is not necessary, but because of the way that we have done our coordinate system, let's just add in the support reactions. Very quickly though, if we summed up all of the forces in the y direction, we'll get a sum of 40 kips going down, and then we'll have our support reactions pointing up, and because of symmetry, it's just going to be half over here and half over here. So we got 20 kips over there. And this will just help us with finding our internal moment equations, which is our second step right here. So we've done first, now we'll go back. So let's just go back to a pretty plain black one. All right, black. And so let's look at member AB. So member AB only has axial forces in it. It only has this 20 kips going up and 10 kips going down. Neither of those will create a moment in member AB. I hope you can see that just by looking at it. If not, I really recommend brushing up on your definitions for internal forces. But anyway, so our first real moment equation, you'll understand why I'm saying real in a second, will be 0. And this bounds will, not that it matters because it's 0, but just to be good practice, the bounds will be from 0 to 180. So let's go to the next moment equation, which will be for x2. I recommend, if we're going to draw this, that we draw the whole frame. We'll just draw a little simple frame here. We got 20 kips here, we got 10 kips here, and then this would be where our section cup, and we'll have our x2 extending from there. So this whole distance, this whole horizontal distance is considered x2. We don't just say that we're cutting, 2/3 down BC and then calculating that. That whole length of that is x2. And then we're trying to get this moment right here. And hopefully you are about at that point where drawing a diagram like this is unnecessary. And we didn't need to do this, but I think it helps just to bookkeeping, better safe than sorry. And nobody likes to make really stupid mistakes, but I will say it's probably wasn't necessary. So hopefully finding the moment equation is something really easy for you. Looking at this member. So we would start out with it being 20 times x, this 20 in the bottom, creating a negative moment at this point. And then we'll have positive moment being created by this. And I know it looks a little confusing because the sign convention, but obviously this is a positive moment. And so if we had just summed the moments at that point, we would have had the 20 be negative and the 10 be positive. But just kind of trying to simplify it, trying to go quickly, but still explain. The bounds on here will be from 0. We'll make sure we'll put x1 here. x2 to 216 inches. And by symmetry, we can tell that M3 is actually exactly the same. Oh, and we can obviously do the algebra here and get 10x for both of them. And the bounds will also be the same because of the way we did our coordinates, and that's why there's symmetry and why this is, don't forget that x, why that makes it easier. And then same thing for M4, which will be from this x4. It is, if you look, symmetrical with our first equation up here, and again it only is having axial forces, none of which would create a moment. So these will also be 0. And this will be our x4. All right. Now, so we've done this. Calculate internal moment equation due to actual load. Done this. Now, what we're going to do is we're going to remove all of the real loads that are on there and apply a unit load in the direction of desired displacement. So if we look back at our question, what is it asking us to do? It's asking us to determine the horizontal deflection at point E. So this is our point E, And horizontal deflection is, and we'll choose the direction of the arrow, which will be kind of like what we think the direction it'll be deflecting in. Just pick a positive deflection going in that way. We'll say it's deflecting that way. Ignore how messy this original one is looking. So this will be step 3. Apply our virtual load. And again, let's just make a real simple wireframe. Just be something like this. And then we have our virtual load at E right here. And so also note this virtual load is unitless. It's just kind of a nice little bookkeeping way to see the effects, but yeah, there's no units. It's not a kip. But so E, if you couldn't tell by the original photo, the support at E is a roller, but the support at A is a pin. So that will cause a horizontal support reaction at A going in the opposite direction. I mean, again, statics, you could go and sum all the forces of X, but I hope you can just look at it and tell. And we are just going to do the same coordinate system that we had before. So this is our x1, this is our x2, this is our x3, this is our x4. And we are now, so we've done that. So now step 4 is calculate the internal moment from this virtual load. So this is our like also kind of non-real moment, but going to do the same process as we did for a real actual loading. But now it's super easy. We just have this one here. Sorry, excuse me. So if we looked at member AB, which is this guy right here, we see we now do have a non-axial force, which would create a moment. So if we were going to section cut somewhere right here, poor drawing of a moment, but that's a little, we lost our section. But yeah, that's our, let's just visualize we're cutting right there, and we want to sum, and we're going to use a baby m, lowercase m, to distinguish between our different moment equations. So that'll be our first one. And that's just equal to 1 times x. So this is causing a negative moment at this section. And the distance is x. I hope I don't have to explain that too much. But, and then we're going to do the same thing for right here, kind of as we did here, keeping the whole picture. And this time, let's not forget our bounds. Even if it's unnecessary, it's good to do. And now for M2, which will be a section cut somewhere between BC, but definitely before where that discontinuity would be. And keep in mind, again, that our moment equations for 2 and 3 will be the same. And because there aren't any discontinuities, if this was a normal problem, we wouldn't have had 2 moment equations. But we're doing this because we have two moment equations right here, or there is a discontinuity. So just because it's maybe not necessary, it's still good to do and keep the same system. So this one over here will just be 180 inches. So sorry. Yeah, this will be 100. Sorry, I was thinking why this one didn't have inches. This one has inches because we're actually multiplying. We actually have a real unit using how far this is from here, from this top part. So that's why there's inches here where this one doesn't. And then again, M3 is also 180 inches positive. And M4 though, it is similar to the first one, except our loading rate here is the opposite direction. So we can guess that it'll not guess, but we can see that it'll just be negative. Make sure to add our bounds, but notice that they're the same as the ones above. All right, and now that we have these two equations, we're going to use this guy down here to calculate the deflection for EX. Let's change colors. I don't know, I love purple. Let's do purple to do our last little equation. So it's the deflection of E in the X direction is going to be equal, and so we have all these different equations, but notice this is 0, and this is 0. So then this guy will be going away because we're just going to be timesing it by 0 and we'll get 0, and this guy will be going away. So we're really actually only looking at these two. And then also notice, in terms of this equation, EI are just constants. They're not they don't have an x variable. Leaving them in the integral does nothing. So I always like to take out constants. And at this point in our equation, while we're doing the calculus, we will just leave them as EI and not worry about the actual values right now. All right, so let's do for the moment equations for the second part, which will be these two guys, and our bounds will be from 0 to 216 inches. So this is where you can see that if we had put 15 feet, our units would be off and we'd be in some big trouble. So we've taken out the EI. Now we have our baby M, our virtual load moment, and that's just going to be 180. And then we'll have our big M, which will be 10x dx, and we'll add that to the next one, which will be for 3, this guy and this guy. It'll also be the same thing. So again, because of symmetry, we could have seen that we could just do it 1 times and then times it by 2. I recommend anytime in a test, if you can do that, do it. You'll save so much time and be able to move quickly. Also, with all of these virtual load equations, if you are given the superposition table, that shows you kind of how to get moment or deflection equations. It's kind of nice to use that as a double check if you're not very comfortable with coming up with moment equations. But just any way you can make this really quick, exams, whatever. I know we're busy. Why waste time if you don't have to? For this though, we will actually write it out. 10x dx. Go ahead. Let's do what I said. So we'll put 2 here. That's as in we'll just kind of only solve 1 time. And I'm not lazy, so I actually like to do my calculus, but I also got into this because I love calculus. If I was a teacher, I would tell you to keep your units on this, but again, lazy, and I know them, and I don't need to. Right, and then just distribute that 10 and the x, and we get 1800x dx. Get this. See if we can just, those constants on the outside, get a number for that. 2 over 29 times 10 to the third. I'm putting this in my own calculator. You guys can too. Or you can take my word. It is a lovely number. 3.73 times 10 to the -8th. Very pretty. All right, and then we'll integrate this buddy. So we get 1800 x squared all over 2. These guys can simplify to 900, and then our bounds are from 216 to 0. This guy will come down times 900 times 216 squared. We don't have to worry about our lower bound, it's just 0, so normally we just subtract 0 if you really want to make sure you did that. So again, just entering this in my calculator, praying it matches what I know the answer is. Alright, it's 1.56 inches. That's our deflection at E. It's positive, so that means our assumed deflection that it's going this way is correct. Nice to make a little arrow. Box our work. Yay. Alright, so the next way we can do it is the graphical method. And now that we have done these moment equations, it'll actually be pretty quick. But I hope you can see that even for the graphical method, we can develop moment equations pretty quickly for kind of simple loadings like this. And you don't need to do as much work as you might have had to do, a few classes ago, or, but at this point, moment equations, it's been done, feel good. All right, scroll down, same problem. Same horizontal deflection at E, so we're going to want to get the exact same answer we just got here, but we're just going to show the differences between these two methods and kind of show you, for this one, graphical is probably definitely quicker. Here's the equation we'll be using at the end to solve for everything. So our first thing we do is create this M over EI diagram, which is just essentially creating a moment diagram and then dividing by EI. And I recommend keeping EI that way. Do not plug in the values, just whatever your usually you'll pretty much will look in this case, look at our whatever our max moment is and just say that's what's divide that. Divide M by EI and keep that simple. How to get to a small pen? Nobody wants a small pen. Alright, so our first job on this one is to do that moment diagram. Let's draw our frame. There's our frame. And if you remember, this is equal to 0, so this is just straight line. This was like our, x and y axis. This would just be constantly at 0. And same thing for the other side. This will also be at 0. Love bigger pens. But we know that this does go up, and we know there's this discontinuity in the middle of that point load, and we only calculated equations that go here. If you remember, it's 10x. So it's just pretty simple line from here to here. This would be 1, this would be not 3, 4, so this is our M2, this is our M3. Alright, now that we've done that, I kind of like to do this a little out of order than the way they do it, so I recommend, not that, it'll all be the same, but for this video, so these are straight lines, so it's very simple load, I'm just not good at drawing, but here is our moment diagrams, and remember this, this top part would be whatever that max moment is divided by E. We would just plug in this value, which is actually, don't let me guess. But so that max value is going to be 10 times this whole distance from B to C or C to D, and that's 216 inches times 10. So our max moment is 2,000 2060 divided by EI, just if you'd like to know. So before we move on and kind of follow their procedure, which might be good to do when you're still doing it, we're going to do some things first with our moment diagrams we have now. First thing we're going to do is find the location of the centroid. Keep switching to the wrong pen. Find the centroid for each of these, noting this discontinuity, so you wouldn't just pick the same, centroid for this whole triangle. It'd be for these two triangles. The location of these is going to be 2/3 the whole distance. So whatever. Am I going the right direction? Yeah, I am going the right direction. Whatever 2/3 of 216 is, which is 144, that distance to that centroid would be 144 inches on both sides. All right, so and the next thing we're going to do is we're going to calculate the areas of both of these triangles. So we'll call it area 2. And we would do the same things for these guys if they actually had areas, but their areas are zeros. I hope you can see that. But anyway, so calculate the area for these triangles. We got a base of 104. No, we do not. Oof. Sorry about that. We got base of 216, and our height is going to be this guy. 2160 over EI, and then all that 1/2. So we get, plug that into our calculator, 233,280 over EI. That's our first area, but again, symmetry, it's also our third area. And that's about everything we would do for our kind of real moment diagrams. We got the areas, we got all we're doing is the location of the centroid. That's all we want to know. And most of your engineering books will have easy calcs on this. I mean, like a square, and it's a like area centroid. So these are just 2D things. Yeah. Pretty simple to calculate. Let's get out our black. And so the next thing we do, just like before that we came up with equations for our real load and then equations for virtual load, we're going to use this figure again it's just a force going in that direction. We're going to use that figure and develop, same frame, develop the moment diagrams for that, for that virtual load. And again, we have the equations, so why not use them? It's this 1x, this is the constant 180, negative x. So this guy, this is our 0, where x equals 0. It'll go all the way up to its max. Should be 180 right here. These guys were a constant 180. Picture that's a straight line. Let me get some water. All right, constant 180, and this guy will be a negative. Doesn't need to be pretty. It's just for us. Negative 180. All right, so now that we got the areas, what we do with those centroids we calculated, and if we were following their procedure exactly, this would be number 6. So, oh no, it'd be actually now 7. We've done that. Number 6 is what we did above. Number 7, calculate the value of this little m at the location of each of the centroids, this location. So that's why I tried to line up both of these frames. So what we would do is just follow this all the way down, and it actually doesn't matter where our centroids are because our value of this is our little baby M is the same throughout that top member. And again, these guys are 0, so they have no centroid location. We kind of are just ignoring them. It's still good practice to do, but yeah, even these guys won't do anything for us at this point, and we're only looking at these top members. So again, the location of where these centroids are at this top part, trace it all the way down here, and see what these values are for little m, not where their centroids are, which, you know, would, if they were in half, its centroid would be over here. That's not to confuse you, but centroid on the real moment diagram, location of that centroid on a real moment diagram, see what that location, what value of little m it gives you. But for ours, whatever location it gives, it's always going to be 180. So our little m value for the first one, which will kind of match with this A2 if you want to look at this equation right here. So our little value is 180, and our other little value is also 180. And that's actually pretty much all we do. It's that easy. And even, you know, if we didn't have this information right here, finding both of these moment equations, I hope, is pretty easy for you. So yeah, we're going to use this guy right here. Here's an explanation of what these means. This is the area, this number that we got here, the area, and this is that value of little m that we found with the location of the centroid, and all we're doing is multiplying these numbers with each other and then summing them up. So what do we like to do the answer in purple? Alright, so our deflection at EX is equal to our area, which is 233,280 over 2910 to the third, 1850. Notice we didn't use this. It's a little tricky, but I think just included if we wanted to determine bending from axial forces, which then would have looked at these members and would have showed you how these members, their axial deflections or deformations cause any bending here, but it would be so little if it did cause a movement this way, and the question tells us to only consider bending, which is what we're doing by looking at these by only looking at our moment equations. All right, so this times the 180 plus same thing again, symmetry, just like the other one. Same equation, just done twice. Go ahead and calculate that, put that into a calculator, and we will see we got the same answer as above. So I think in general the graphical method is easier unless you're going to have, well, and yeah, that's all I'll say.